Okay, we have this function, and the question is asking for the evaluating this uh, this function. I don't I don't really want to use any techniques, any trick here. What is important for me is that use the relation between the definite integral and area. So for that, I have to first draw or sketch the graph of this function. Um, I will do it here because it's definitely. So how do I sketch this guy here? So this is absolute value of x. Everyone knows absolute value of x. This is our corner guy. And then this x minus 1, um, x minus 1 means that we have to shift it 1 unit to the right. Then there is a minus sign here. That means that we have to find its reflection under the x-axis. So about the x-axis. So that is going to be a reflection. And then there's plus 1 there. And plus 1 means that you have to shift it 1 unit up. So if I shift that 1 unit up, this will be what we have. But you have to be careful. This is the formula for our function only, sorry, only on the interval 0 to 2. And if you do follow or trace the points that we are shifting and doing the transformation, this is 0, this is 1, and this will be 1 as well. This is 2. And everything else must go away. So this will go away here. This will go away. And I have just that tenth there. How about this one here, the second formula? Remember that we had this r squared minus x squared. This was semicircle. If there is upper semicircle, if there is a minus there, that's lower semicircle. And if you transfer that semicircle to the right a unit, this is the formula you will get. Lower semicircle centered at A0, and then the radius is R. Here, when you look, I don't see that pattern, but I can turn negative 12, I can do it somewhere here, negative 12 plus 8x minus x squared. I can first factor out that minus sign. Let me just reorder them a little bit. Actually, I can do that way. Okay, so 12 minus 8x plus x squared. And then completing square, that's what we do. Here's x minus 8 x, a squared minus 2ab plus b squared. So I can see that this must be of this form. But in that case, I need 16 here. There is only 12 there. That means that I have to add 4 to that 12 to make it 16. But on the other hand, I have to subtract that and 4 that I added to generate 12. So this way, what we have here is basically that then multiply that negative sign inside. So this is 4 minus x minus 4 squared. What is this? This is lower semicircle centered at 4 and 0. I shifted everything 4 unit. And what is this? This is square of this radius. So with radius 2. Let's sketch that graph. So this is 4. This is 2, 3, 4. Then semicircle down there. The radius is 2. So if we start from here, I will go up right there. Okay. Now that we have everything there, I will go and look at the integrals that I have to evaluate. Integral of the function from 0 to 1. Well, from 0 to 1, I only have this piece here. And if you look, that is positive side. Since I will use this one lower down there, let me just copy and paste this so that I have access to that. Oops, where did it go? Ooh. Okay, I will use this one here. But for now, what we have, this one here, is that, okay, I just want to use 0 to 1. And that just involves this region that you see. It's above x-axis. That means that the integral of f from 0 to 1 is nothing but area of that triangle, starting from 0 going to 1, and its height is 1. So it is half of height times the base. That is. For the second one, we go from 1 to 4. So 1 to 4. And if I fill in the region between the x-axis and the graph of the function, I see that there are 2 regions. One region is above x-axis, so integral of the function from 1 to 4, I have to separate it into 2 pieces. The positive side is this small triangle, this 1, 2, and the height is 1. And then the other part is 1/4 or quarter of a circle, and it is under the x-axis. So I have to first do minus area of that quarter of circle of radius 2. Well, I know how to find the area of that circle. It's half of the height times base. Base is 1 minus area of the circle of radius 2 is pi 2 squared. But this is only quarter of that, so divided by. Yeah. So this way we have found that the area is the integral of the function from 1 to 4 is 1 half minus pi. Note that I'm not using any integration tool. I'm not using the Riemann sum. I'm just using the relation between the definite integral and the area of the regions between the graph of function and the x-axis.